left, which I've now erased conveniently, you can look and go, oh, there's fluoride, oh, there's non-fluoride. So you can see the difference. Here, it's like, okay, what am I looking at? This is why you have to go back and read the studies. Look at how they set up their study. They will tell you what got subtracted from what. So if they say we took X bar 1, which was the sample IQ of the fluoride kids, and X bar 2, which was the sample IQ of the non-fluoride kids, and subtracted it in that order, X bar 1 minus X bar 2, then you'll know. If those things come up negative, the IQs were lower in the fluoride kids. If they, just by definition of the subtract, this is the mathematics of the statistic, not if it's actually worth looking at, but it's the mathematics. And we're going to look at this a lot in this class, the back half of this class. Fair-ish, maybe. Okay. Now, I want to go back to this again. So suppose now, we've done the study this way. And don't worry too much about that right now, JC. It's not that crucial at this point. Honestly, it's not. Here's the deal. Suppose we're back to the study that we just looked at, which was IQ is worse for kids with fluoride and fluoridated water versus non-fluoridated water. Don't mind the fact that their teeth are falling out. Their IQs are worse. I'm sorry. I shouldn't let that slide. My fault. There it is. That supports that study, yes? That supports that study. Because assuming we subtracted it in the way, this is below 0, which means there's a statistically significant change. I don't know how much the change is. It might be meaningless. It might be practically meaningless, but it's not touching 0, so it's statistically significant. Now, what do you want to do if you want to replicate the study?
Yeah, you follow their methods in their study.
See, that doesn't help.
With a different researcher.
Different researcher, but you
Follow the same method.
follow the same protocol. This is very often ignored. If you ever look at a study in your journals where they take a whole bunch of studies and put them together into one and say, well, we did a correlation or a collection of a number of studies. And first of all, is that legit? Are all the studies done exactly the same way? The answer, as Janji's saying, might be no. So you have to follow the exact same protocol and follow the exact same stringent, different researcher, definitely, hopefully one not tied to either the fluoride industry or anybody making an IQ test, obviously. And let's suppose the next study comes back and the confidence interval looks like this. It's tighter because the sample is larger, perhaps. It's okay to have different sample sizes, of course. That's totally fine. Okay? And then the next study comes back and it looks like this. Are all of these intervals supporting the hypothesis that fluoride in the water lowers IQ? Not saying it's a correct cause-effect, but are they all supporting that hypothesis? Looks like it, right? Why do I feel better when I see 3 studies all saying the same thing versus just one? Mathematically, why do I feel better? I like that. But technically, statistically, it's the same population we're studying, though, isn't it? It's a larger sample. It's a larger sample, so technically the margin of error is shrinking. Okay, so technically the margin of error is shrinking. But suppose we're not throwing them all together into one. We're looking at 3 different ones. I like that very much. Kate, go.
I was just saying it's 3 different samples, probably from different situations.
It better be. If it's not, then I ignore the other 2. It better be.
Yeah.
Go.
And what I was going to say, not necessarily as far as what she's going to say, but in order for any statistical experiment or anything to be valid, it has to be able to be peer-reviewed and get the same results, or it doesn't mean anything.
And hopefully your peers actually understand what you're doing too. Yeah, that's a big problem these days.
If you do something and you're able to, put a piece of meat on a plate and maggots come out of it, and you go, oh, meat creates life.
Meat creates
but
maggots.
then nobody else can do it, it doesn't mean anything.
Which I think actually happened a couple hundred years ago. Lauren, go. I want to hear from Angie. I want to hear from Scott, from all you guys. Go.
Multiply by 3
Even better than multiplication by 3. Hold that thought. Hold that thought, please. Angie, go.
I was just going to say, statistically, it would be difficult for all 3 of them to get outliers that are pulling it the wrong direction.
I want to rephrase that if it's okay, Angie. It's perfectly correct. Skylar, go.
I was just going to say it's important to replicate it because there was a study published saying that autism is caused by vaccinations, and then people didn't vaccinate their kids.
One study that was never looked at most carefully enough to realize that it was complete and total bunk. People believed it for years and years and years and years that vaccines cause autism. I know they do. Because old habits die hard. Because it's so... And you think about it, what goes into a vaccination? A screaming child, a sharp object. We have these unintentional human biases built into it too. We don't like it already. And all we have is that tipping point of, oh, now we don't have to get them vaccinated because it'll cause autism. Unless you read the study, which doesn't prove anything. Thank you for that. Thank you for that. Angie and Lauren, I want to paraphrase mathematically before our break why replication makes so much sense. I draw a line out from the blue one here. What's the chance that we are right? And I'm putting that in quotes. When I say right, what's the chance that that interval actually captures what we're looking for? 95%, yes?
So if you do 5 over 100 times 5 over 100 times 5 over 100.
Yes. That's why I didn't want to say multiply by 3, but raised to the power. So you guys, after one study, there's a 95% chance you caught the parameter you're looking for. There's a 5% chance you missed it, yeah? Fair enough?
So your chance of getting wrong, it gets smaller and smaller.
Yes,
smaller.
that's the point. The chance of all of them being wrong gets smaller and smaller and smaller. Now here's the deal now. Suppose you do it twice. Yes? Suppose you do it twice. I want to ignore the chance of being right. Let's just focus on the chance of being wrong. Because at this point, you've seen the same result twice. The only thing you're nervous about is what's the chance they're both wrong? Check this out, right? What's the chance this was wrong? 1 over 20, 5%. What's the chance this was wrong? 1 over 20 again, 5%. So the chance they're both wrong is 5% squared, which is 1 in 400. It went from 1 in 20 to 1 in 400. And if you see it a third time, it's going to be 1 in 8,000.
Didn't you literally just tell us that when you do more than one, you're multiplying 95%?
That's that they're all right.
Okay.
But when you start seeing a study supported like this one, the question you should be asking are they all wrong? Because that's the only time you'd expect one in a while to be wrong, of course. Because the same logic mathematically applies to the 95%. The chance that they're all right is 95% squared. That's still pretty damn high. 95 times 95 is 90. It's still fairly high, but the chance of both of them being wrong is falling away towards 0 very, very quickly. Now, the problem is that 95% confidence was applied to stacking intervals into the same study. This is the study itself being compared on different levels in a different study, different study, different study. You see the slight difference in not mathematics, same mathematics, but a difference in the theme of what's actually going on. So mathematically, you want replication because, yeah, you are going to get outlier results. There's a great article I read called "The Truth Wears Thin" or "The Truth Falls Apart" years ago, and they lamented the fact of all these studies being published that are then overturned in the journals. Well, hell, I hope so. That's not 100%, that's 95%. 1 in 20 articles should fall apart just by random fact. In other words, they got a false positive.
But maybe even more, because maybe people publish
Yes.
too much.
Maybe people publish they shouldn't be publishing.
Perfect situation with zero
Yeah.
bias. And
Oh, of course, of course. So, and I'm giving them the benefit of the doubt. The thing is that the numbers they were talking about weren't that high. I mean, if you think about the number of papers that are published every year with positive test results, hell, 1 out of 20 of those, that's still a pretty big number. So they're saying, oh my God, hundreds of articles last year. I'm like, I hope so. Because that means statistics is working, as we know it does. Well, and the scientific method. The papers I have been reading recently, though, is that, and this is why I'm so glad you guys are sitting here with me in this class, you're learning about the method itself, rather than just some preconceived handed-down notion of what mathematics is going on. You're learning the mathematics, too. That's huge. I know I shirk the formulas quite a bit. I like shirking the formulas. Until the very basic ones, like the multiplication of probabilities, like taking an average, a z-score, those we can't shirk, and we will not shirk, as we didn't do them in 243 either. So those we're going to see time and time again. I've tried to weed out the formulas like Chebyshev's. Like, honestly, I mean, Russian's awesome, da, comrade, but honestly, it's not that valuable. A z-score, infinitely valuable, infinitely, and part of the construction here. Kate, and then we'll take our break. Yes, go ahead. No, you go.
Let's say you had a study that showed that it touches the 0.
Oh,
It touches
good.
the average. How many-
Can we come back to that? No, that's a great question with a very long answer.
Okay.
And we will come, I promise we'll come back to that. Again and again and again, yeah. That's when is statistical significance almost there?
Well, it's how many studies would
Well,
be-
mathematically you can figure it out, can't you?
Yeah.
Just let that be a variable. Like you did, it's 243, it's the pumpkin seed problem in 243. How many pumpkin seeds do you have to plant to be?
I hated that. Thank you. I hated
I
that.
found it very valid and useful.
Two to
I like
1.
2 to 1. That's confirmation bias, Megan. That is confirmation bias. I'm not about to question the class, because that's
I didn't like
engagement
it.
bias. I'm making up a word here. Whether you liked it or not is regardless. Whether you liked it or not is regardless. The important thing is the mathematics behind it answers Kate's question. How many do you have to do until you're a certain level of confidence that at least something is working?
Disregard.
Yes.
Okay.
Yeah. Do you guys save documents in your My Documents folder at school?
Not that one, no, because it.
Not the pumpkin one? Of course, it doesn't exist. Do you save your documents in My Documents at school?
The sooner the least.
Then you like the pumpkin
I'm
problem.
serious, like, you like on real big.
Let's take 5. Let's take 5, get some air, get some water, and we'll come back and talk more about this. This is good. Good discussions, good discussions. We have not